Friends, I'm Aoife, and today I'm going to present this project, which is on modelling of the wake effect for wind farm control using neural networks. So first off, the problem. The wake effect, as I just mentioned, is a tricky phenomenon. Here we have a wind farm. That's a collection of wind turbines, like my friend Windy, the wind turbine here. This is not to scale, but I couldn't get a bigger one from NREL for the purposes of this presentation, so we'll have to make do. When the free stream wind speed, so that's the normal wind speed outside of the wind farm, hits these first few rows of turbines, we call them the upstream wind turbines, it's a wonderful wind speed by all accounts. It's fast, high velocity, low turbulence, smooth. The problem is this wake effect you see behind these first few wind turbines. That's turbulent, chaotic, lower velocity, and those downstream turbines behind the front rows have to contend with that. And what this means is because of these wakes, the overall wind farm doesn't produce as much energy as it could because of the lower quality wind field experienced by those downstream turbines. And it also results in higher damage for the turbines because this wake is more turbulent. So not good all around. That's me trying to control a wind farm and combat climate change and failing because of this problem. So the second part to this problem is wind farm control. So that primarily means yaw angle adjustment. So if we take Wendy here, yaw angle would be rotating this way or that way, and what that does is deflect the wake behind Wendy to not hit the turbines directly behind Wendy, which is a good thing, and that means less turbine damage, more total power generated, and happy wind turbine operators and control engineers like myself. So what is it we're trying to model here? We have inputs and outputs, as with every model. Those inputs are the free stream wind direction, so that's the kind of average wind direction outside of the wind farm at that time. The upstream turbine wind speed, so that's the wind speeds experienced by the turbine, the first few rows of wind turbines that the wind hits. And then the control set points, we'll say, for those upstream wind turbines. So that's the yaw angle, as I mentioned before. And also something called the axial induction factor, which changes what proportion of the wind's energy that turbine extracts. We can plug all of these into this magic wake effect model, and ideally we want it to output the wind speeds at those downstream wind turbines. So we can predict, given some historic amount of data, what the wind speed will be at those downstream wind turbines. And if we know that, we know we can have a better idea of which way we should yaw or rotate those upstream turbines to deflect the wakes. So that kind of sounds like time series forecasting, which suggests that recurrent neural networks would be a potential solution. And that's me when I heard about them. Let's walk through what a recurrent neural network is from the ground up. We'll start with a single recurrent neuron. So this is the condensed version on the left. We have a neuron that has weights and biases, a weight and bias and an activation function. And it doesn't just have an input X and an output Y, but it also holds on to this hidden state, which is fed back into the neuron over multiple time steps. So the unrolled version over multiple time steps is here on the right. And we see at each time step, we feed it this neuron an input, get the output, and feed that hidden state to the neuron again with the next input, and we get the next output, and so on. We can then expand that single neuron into a single recurrent layer. So that means in this case we have 5 neurons. In this case we're using the ReLU activation function. And they're all in a single layer. They all receive the input at each time step, and they all are combined to generate the output for each time step. And then in this case, the output is the same as the hidden state, which is fed back into all of those neurons. And again, you see this unrolled version on the right, where that hidden state is passed on to each layer. we can expand this single recurrent layer again to make what we call deep recurrent neural networks, where we can stack several of these layers on top of each other for each time step. And again, you see the hidden state is passed on from one layer to the next over multiple time steps. We get outputs for multiple time steps, and we have inputs for multiple time steps. In this project, two different types of recurrent cells are used. The first one is the long short-term memory cell, or LSTM cell. And what this does is allows the neuron to hold on to memory of what happened with previous inputs and to decide how much it should remember from the past to predict current or future values. So we have a few different variables here. We have the long-term state C, the short-term state H, the input vector X. G is the output of the recurrent neuron, which is just like the perceptron we did at the beginning of this course, the output of a standard neuron. And Y is the overall output of this LSTM cell. These cells also have three gates, we call them, which the forget, the input, and the output gate, where the first one, the forget gate, controls how much of the long-term state is erased. The input gate controls how much of that recurrent neuron output is added to that long-term state, and the output state or gate determines how much of the long-term state is included in the overall cell output and also in the short-term state. The second cell tested in this project is the gated recurrent unit or GRU cell, which is a simplified version of LSTM. In this case, the long-term and short-term states are combined into a single hidden state H, and there are only two gates. The update gate, which controls how much of the hidden state versus the recurrent neuron output is added to that hidden state, and the reset gate, which determines how much of the hidden state is considered for that neuron output G. Another variable we look at here is how to predict not just the next time step, but the next 60 seconds, say, of downstream wind turbine values. So there are two approaches for doing this tested in this project. The first is called multi-step RNN predictions, where at each time step, the model predicts the next 60 seconds of data. So at 0, we predict the next 60 seconds, 1 to 60. At 1, we predict 61 to, or we predict 2 to 61, and so on. And this allows for more derivatives and more values to be computed and propagated back. And we're basically predicting the next 60 seconds of data with a single prediction. The next approach is called autoregressive RNN predictions, where a single prediction just predicts the next time step, but that's then fed back into the model sequentially to produce the next, in this case, future time horizon of 60 seconds of data. Another thing considered is absolute versus residual predictions. So absolute predictions, the model outputs the downstream wind speeds as they are. With residual predictions, the model outputs the difference between the last wind speeds and the current time step wind speeds, and then those can be added together to get the overall downstream wind speeds. So if we look at the results, I'll just give you a snippet of it, and you can look at my website for more detailed results. They're not good. So really a persistent model that just used the most recent value to predict the next 60 seconds probably would have been as good, if not better. So why did hours of training do no better than extrapolation? Well, the code runs and the logic is sound. A hypothesis is that some parameters need to be tuned, that the architectures need to be adjusted, perhaps with some dropout layers and less neurons, so that the training data is not overfit. Also to include more training data. In this work, 10 hours worth of data were used, but perhaps more is needed. And also the losses need to be considered carefully in terms of what outputs are considered in the losses only the last ones or those over every time step. So there are some things to look at. Wendy and I are grateful that you attended this talk today. Please leave a 5-star review. Testing, testing, testing. Can you hear me? Testing, testing, testing.